Hello everyone, today we have a new case study. We will perform a structure analysis on a sheet metal part. So we will see how to define shell element on the part with part thickness. We will apply fixed geometry on edges and remote load. And finally we will apply a curvature-based mesh with these specifications. So here I have already opened our part file. So I will create a new study, go to SolidWorks Simulation, Simulation tab, and new study. I will set the name to sheet metal. Okay, so first, as usual, we begin by assigning the material. So we right click on the part name, apply material. We search for AISI 1020 in the library, and once selected, we apply. Okay, so now we will define the shell element. To do this, we right click on the part name, go to define shell by selected faces. So I will choose those faces here because later we have to apply a load on this face. Okay, for the part thickness, it's automatically detected. Okay, so here we have our shell. So now we go to fixtures, fixed geometry. We clear this. So we zoom in to get the edges. And now we define the load, so go external loads, remote load or mass. We select the face. So we choose the global reference coordinate system, and for the location we have -100 along x and -40 along y-axis. For the translational components, we enter 30 newtons along y-axis. Okay, so for the mesh, we go to create mesh. Mesh parameters, we select curvature-based mesh, and we set the maximum element size to 2 millimeters and the minimum to 0.1. And here we have our part ready for the simulation. You can see it's in 2D due to the shell element we defined earlier. So now we run the study. Okay, so to check the maximum stress in pounds per square inch, we right click on stress, edit definition, and we change the units to PSI. We select the max annotation, and we change the number format to floating, and we adjust the decimal places to 3. Okay, so the max stress is located here. So now comparing this to the material's yield strength, which is 50,000 psi, we can see the stress recorded is well below the yield strength, so the part remains in its elastic range, meaning it will return to its original shape once the load is removed, so no permanent deformation. As for the deformation, the simulation exaggerates it for better visualization. In reality, the displacement would be much smaller. We can change it to true scale. And here we go. So we can see the part bends slightly, especially in the upper region where the force is applied, while the fixed edges restrict movement, causing stress concentration zones here in red. So overall, the part holds up well under this load, but there may be room for improvement, especially in reducing stress concentrations around the constraints. That's it for this tutorial. Don't forget to like, share and subscribe for more simulation content, and see you in the next video.